right. So you've seen in the last couple segments how these problems really rely on you being able to go back to the fundamentals. Now, what you want to be able to do, as I said earlier today, is you want to be able to take this trig material you know and start to apply it to situations that might be real, more real than maybe just being given an equation out of a book and solving it. So I've got a couple little items that we could do. Let's look back. Why don't we look back on page 452 for a second. Way back at 452. And this is kind of a classic problem that shows up in most pre-calculus textbooks. And what I'm going to do is just summarize it here on the board. Number 76 on page 452. What we're doing is we're standing back from a screen. It could be you folks looking up at that monitor up on the wall up there. Notice that the bottom of that monitor is above your eye level. Or you're at a movie theater where the screen is sitting up above you, above your eye level. So your eye is over here. Here's your eye. And you're looking at a screen that is sitting up there above your eye level. Now this one, they've given some particular problem, or they've given some particular dimensions to this screen. This is a pretty tall screen. It's 28 feet tall. And it happens to be sitting 6 feet above our eye level. 6 feet above our eye level. Right there. And what we want to do, the objective here, every time you go in a movie theater now, you're going to think about this, okay? Your objective is to place yourself at a distance x back here from the screen in such a way that the angle, your eye angle, is the widest. Your viewing angle is the widest. Now imagine that you're sitting out here 500 feet. You're at a concert. And they've got one of those screens up on the stage behind the performers because you can't see the performers because they're about an inch tall, okay? So they got this big screen sitting back there. Well, if you're sitting way back, isn't your viewing angle even of that screen still very tiny? Way back over here, your very tiny angle, okay? And then as you come in closer, that angle widens, doesn't it? Now let's keep coming in closer. How many of you like to sit in the front row at a theater?
Never.
I know people that do. I don't particularly care for it. But anyway, you get in here and what happens to that angle? It starts collapsing on you, doesn't it? So doesn't it make sense that there is some appropriate distance out here that's going to give you the widest viewing angle? Okay. Now the book defined that viewing angle as theta. That viewing angle as theta. And back in the book, they actually give you the equation that describes that theta as a function of x. Or excuse me, x as a function of theta. I don't know, which way did they give it to us? They gave us theta as a function of x. So that's our objective, is let's come up with theta as a function of distance x that we are back from the screen. And see if we can find out, let's figure out what that thing is. Now, at that point in the book, they gave it to us, but I want to show you. You know enough trig now to build this formula. And then, let's go ahead and use our calculators then to solve this for the maximum viewing angle. So we're looking also for theta max. Maximum viewing angle. Now, I want to go through this kind of quickly because I'd like to do more than just one application problem with you, and we only have a few minutes left. So, what I want to do is I want to define, let's define this whole angle. Why don't we call that whole big angle, let's say beta. And let's call the little bottom angle right here, let's say angle alpha. All right? So what is theta? in terms of alpha and beta? Beta, the whole angle, minus angle alpha, right? So theta equals beta minus alpha. Theta equals beta minus alpha. All right? Now come back and look at angle beta for a second. Big beta. Total height right here is 34 feet, isn't it? Yeah. And this distance right here is x. Do you have a trig ratio that can tell you something about beta? What is it? Tangent, isn't it? Tangent. So the tangent of beta is equal to 34 over x. What's beta?
Beta plus alpha.
Now I want to solve this for beta. Beta equals?
The inverse tangent.
Ah, thank you. Inverse tangent of 34 over x. Right? Not too tough. Once you did this, once you'd studied a little bit about inverses. Let's come back and look at the smaller triangle down here in the bottom. The smaller triangle on the bottom has angle alpha in it, and it's got a height right there on the far side, opposite side of 6, adjacent side of x. So similarly, alpha is
The inverse tangent of 6 over x.
good. Inverse tangent of 6 over x. So now come back up to the problem up here. Theta as a function of x is going to be the inverse tangent of 34 over x minus the inverse tangent of 6 over x. An angle minus an angle is equal to the viewing angle. When you take calculus, you will be able to solve this problem. But we're in trig. We can solve this problem right here graphically, where we plot theta as a function of x versus x. And this viewing angle could be as small as 0 degrees way back here, right? It gets bigger and bigger and bigger, and then as you get up closer and closer and closer, it comes back towards 0 degrees, doesn't it? That viewing angle. So we should expect at infinity, at a huge distance, we should expect the viewing angle to be dropping off to a very small value. And back here near x equaling 0, we should expect a number close to 0 viewing angle. And we should see somewhere in here where the viewing angle at a certain critical x, a critical x value, there is a maximum viewing angle. Make sense? So let's see what happens. And let's go ahead and be in degree mode. So we go into our calculator. I think I'm still in degree mode. I go to y equals, and I'm going to pop this equation in, inverse tangent of 34 over x, and that should agree with what's in the book, and we're subtracting from it the inverse tangent of 6 over x. And then we need to set an intelligent viewing window. I hope you folks have moved away from using that thing I call the stupid window, which is minus 10 to 10 on dimensions. I don't even know why they put that, make that available in the calculator, because there's not much stuff in the real world that fits in that range. So let's go on degree measure. I'm sorry, x represents distance, doesn't it? Yeah, so 0, and our distances that we have for that screen is like 28, 34 feet. So why don't we say, if it was 34 feet for x, that'd be a 45 degree beta angle, wouldn't it? Let's let it go out further. So let's say it goes from 0 to say 80 feet. 80 feet, and put tick marks every 10 feet. That makes sense? And then vertically represents our viewing angle in degrees. So what kind of range of values might you want to use here for the minimum on Y? Why don't I put minus 20 degrees to 60 degrees and put tick marks every 10 degrees. Just jot those 6 numbers down if you wish. Here comes the graph. Okay, very slick. This reminds me of what we call a surge function in mathematics, where something surges up to a peak value and then it takes a while for it to then diminish out. There are other equations, not trigonometric, that'll have this characteristic. And so what we could then do is use our calculate features to seek the maximum, item number 4. We've done this before with you. I can look at my scaling here. This is in feet, right? 10, 20, 30, 40. It looks like between 10 and 20 feet. So if I make a left bound maybe at 10 and a right bound, see that leaves a little arrow up there, right bound maybe at, why don't I say 30, just for the heck of it, and then maybe guess 20 and let it work, and it's going to come back and give us the answer at 14.28 feet. Where are we? So what we ended up getting here is a graph that looks like this, and so this critical value here is 14.28 feet away from the screen, and our maximum viewing angle is 44.43 degrees. Pretty interesting, huh? Okay. This is called an optimization problem. You're trying to optimize your positioning to get the maximum viewing angle. In calculus, you will learn how to find the place where this graph has a zero slope. A zero slope. It's called the first derivative. Where the slope is 0 is where that maximum occurs. Okay, let's do another problem. Why don't we go over to page 484. 484, and this is a geometry problem, and it's going to take us back to some knowledge from our algebra background. Number 86 on 484. We have a semicircle that's the top half of our unit circle. Top half of our unit circle. So it's a radius 1. And what we want to do is we want to build a symmetric rectangle inside that semicircle. Inside that semicircle. And we are going to label this dimension x. And this distance right over here is also x because of the symmetry. And what we want to do is figure out the area of the rectangle as a function of angle theta, where theta is that angle. And you know that these points on the circle could be labeled x and y, which correspond to your cosine reading, right, of theta, because it's a unit circle. And your height right there is the...
How do you know it's a unit circle?
They told us.
Okay, you're right.
Okay. And the height right there is the sine of that angle theta. So we're trying to find the area of this rectangle the area of this rectangle as a function of theta. It should make sense to you if theta is 0 degrees or near 0 degrees, you're going to get a very long, very flat rectangle with no area. And if theta is near 90 degrees, you're going to get a very tall, skinny looking rectangle. Essentially of 0, okay? So, look at the area. What's the base? What's the length of that base?
2x.
2x, but x is 2 cosine theta, isn't it? Because this x leg here is cosine theta. So the base is 2 cosine theta, and the height is sine theta. And there it is. There's the area as a function of theta. But look at this, folks. 2 sine theta cos theta. 2 sine theta cos theta.
Oh,
your-
tangent.
No? Is your memory kicking in?
No.
That's the double angle formula.
Yeah.
Thank you. That's the sine of twice theta. So the area as a function of theta is sine of twice theta. Okay, we'll be done here in just a second. We're trying to figure out the angle that'll give us the largest area inside there for that rectangle. The largest, what theta would you pick to get not the little flat one, not the tall skinny one, but one that's just right, that has the biggest area?
Radical 2 over 2.
Let's see. Ty thinks it's radical 2 over 2 for the ratio. Okay, so we know, hey, we don't even need our calculator on this one, do we? Draw it. 0 to 90 degrees. What's the period of this thing, this sine wave? It's 180, isn't it? 180 degrees, right? So the period of it is 180 degrees, so up it goes and down it goes, right? And look at what Ty suggested. I think your thinking was correct. Right there. Isn't that where this thing peaks out? This is your maximum area right here at 45 degrees. So what you would do then is you would come into your semicircle, and pretty much like I drew it here, you draw your angle at 45 degrees, and then you've got your x dimensions and your y dimensions, and it gives you your maximum area. And what's the maximum area? A at 45 degrees. What is that answer? Sine of 2 times 45. What's the area? Help me. Sine of 90? 1. Might be square units or square feet. Could be square feet for A max.
You could have just told that from the first picture that you drew, though. From the first picture you drew, you put the tangent at 1. I know that sine is square root of 2 over 2.
Yes, that's what Ty was saying. And square root of 2 over 2, and this is square root of 2 over 2.
Yeah.
And so then figure out that area, base and height, and you'd get 1. But we just did it graphically and deduced the solution from this graph. Okay, that shows you a little bit, a glimpse of applications, and we'll do more of this stuff in the future. We'll see you tomorrow, I believe.